Getting to know the R8C 2A and 2B group MCUs by Renesas. Welcome to the training module on Renesas' Getting to know the R8C 2A and 2B group MCUs. This training module provides an introduction to the R8C 2A and 2B series of MCUs. The R8C 2A group and R8C 2B group of single-chip MCUs incorporate the R8C Tiny Series CPU core, employing sophisticated instructions for a high level of efficiency. With 1 megabyte of address space, it is capable of executing instructions at high speed. Power consumption is low, and the supported operating modes allow additional power control. These MCUs also use an anti-noise configuration to reduce emissions of electromagnetic noise and are designed to withstand EMI. Integration of many peripheral functions, including multi-timer and serial interface, reduces the number of system components. The difference between the R8C 2A group and R8C 2B group is only the presence or absence of data flash. Yet peripheral functions are the same. Here is a block diagram of the R8C 2A and 2B groups. These MCUs incorporate the R8C Tiny Series CPU core, high-speed on-chip oscillators, a 10-bit analog-to-digital converter, an 8-bit digital-to-analog converter, multifunction timers, different communication interfaces, and up to 128 KB flash of memory and 7.5 KB RAM. This slide lists the R8C 2A and 2B group's key features and benefits. The M16C platform's compatibility for more design choices allows for the reuse of application code and developmental tools. The high-efficient code makes these MCUs have more flexible addressing modes and saves memory capacity. The MCUs have 3 operating modes: normal, wait, and stop. To save power, the peripheral functions can be turned off when they are not in use. This kind of low-power operation can extend battery operating time, which is important in portable devices. The fail-safe operation enhances the reliability of the embedded systems. The internal flash memory with fast write or erase speeds enable the code to be easily changed in development, manufacturing, or in the field. Finally, these MCUs have many useful on-chip peripheral functions that decrease system chip count and reduce total system cost. The flash memory can be programmed and reprogrammed off the board using a serial programmer. It can also be erased and rewritten when the MCU is mounted on the circuit board. The on-chip flash is in-system programmable via the boot and user programming modes. In the boot mode, the boot program built into the chip is called up to erase and then program the entire flash memory. New data to be programmed into the flash is obtained from the serial port. In the user mode, individual flash memory blocks can be erased or programmed under the control of a user program. These group MCUs provide protection against accidental writes or erases of the flash, which is accomplished by an ID code function. The MCU has 2 8-bit timers with 8-bit prescalers, 3 16-bit timers, and a timer with a 4-bit counter and an 8-bit counter. The 2 8-bit timers with 8-bit prescalers are timer RA and timer RB. These timers contain a reload register to store the default value of the counter. The 3 16-bit timers is timer RC, timer RD, and timer RF, and have input capture and output compare functions. The 4-bit and 8-bit counters are timer RE and has an output compare function. All the timers operate independently. The table shows the functional comparison of the timers. The serial interface consists of 3 channels, UART0 through UART2. Each UART has an exclusive timer to generate the transfer clock and operates independently. Each UART has 2 modes, clock synchronous serial I/O mode and clock asynchronous serial I/O mode. In clock synchronous serial I/O mode, data is transmitted and received using a transfer clock. In clock asynchronous serial I/O mode, the UART allows data transmission and reception after setting the desired bit rate and transfer data format. When reading data from the use of IRB register, where I equals 0, 1, or 2, either in the clock synchronous serial I/O mode or in the clock asynchronous serial I/O mode, ensure that the data is read in 16-bit unit. LIN is a communication and distributed processing bus system. It is characterized by a low-cost hardware, a relatively low data transmission speed, and a number of bus nodes. Distributed processing with LIN supports the reuse of hardware modules in multiple products. In LIN, almost all functionality is done by the firmware. LIN makes the scale tip in favor of distributed processing due to its low per device hardware cost. The hardware LIN performs LIN communication in cooperation with timer RA and UART0. The MCUs have three operating modes: normal, wait, and stop. In normal mode, the device is fully operational. However, the main clock can be divided down by 2, 4, 8, and 16 so that the CPU core and peripherals can run at less than full speed to conserve power. In wait mode, the CPU is turned off and all peripherals can operate either on the main clock or on the R8C oscillator. Power consumption can be up to 99% less than it is in normal mode. In stop mode, the CPU and peripherals can be put into a deep standby condition, reducing power to an absolute minimum. To save power, the peripheral functions can be turned off when they are not in use. Moreover, when the A to D converter isn't being used, the software can even turn off the circuit that generates the converter's reference voltage, thereby eliminating current flow from the V reference pin into the resistor ladder. In addition, all of 8-bit timers are able to operate in timer mode. In this mode, the timers can function independently for counting without using the base oscillator. When using the on-chip debugger to develop and debug programs for the R8C 2A and 2B group, take note of the following. 1. Do not access the related UART1 registers. 2. Some of the user flash memory and RAM areas are used by the on-chip debugger. These areas cannot be accessed by the user. 3. Do not set the address match interrupt. 4. Do not use the BRK instruction in a user system. And finally, 5. Debugging is available under the condition of supply voltage 2.7 to 5.5 volts. Debugging with the on-chip debugger under less than 2.7 volt is not allowed.